Hi everyone, I'm Ziche Liu, a junior from the Chinese University of Hong Kong, Shenzhen. Thank you for joining. Today I'm excited to present you our work titled Take the Essence and Discard the Dross, a rethinking on data selection for fine-tuning large language models. The work is done with great support from Rui Ke, Yajiao Liu, Dr. Feng Jiang, and Professor Haizhou Li. Recent research highlights that data quality matters more than quantity for effective fine-tuning. And therefore, many data curation techniques have been proposed. For example, data evolution improves data quality by prompting a LLM to generate higher quality samples from a small set of seeds. And then data reflection typically performs iterative refinement on the given dataset to improve data quality. And finally, our focus today, data selection. Formally, data selection selects from a candidate dataset based on a set of specific selection criteria to obtain a high-quality subset. Fine-tuning a model on the entire candidate dataset results in a baseline model called the BLM, while fine-tuning a model on the high-quality subset results in a selective enhanced model called SEM. And SEM should outperform the BLM if done right. This selection paradigm enhances the model's performance while improving training efficiency. However, despite the rapid development of data selection methods, currently there isn't a unified framework that can systematically categorize and evaluate these selection methods. Existing high-level surveys have reviewed data selection from the perspective of all three training stages. But they generally lack in-depth discussions of the fine-tuning stage in specific, and this gap makes it difficult for researchers to conduct more focused studies on this crucial phase. Therefore, we propose, first, a novel three-stage scheme that consists of feature extraction, criteria design, and selector evaluation. The scheme will help us systematically categorize and evaluate these data selection methods. Starting with feature extraction, based on the different transformations applied to the candidate dataset, we divide the features into these three types. Works that use human design features tend to transform the candidate dataset into human explainable features based on linguistic information like helpfulness of a response. However, if you want a more direct and targeted selection, model-oriented features will be a better choice because they are extracted from the backbone model and will help select samples that can directly minimize the model's loss. And finally, some works just use the original text because raw data usually preserves the most comprehensive information. Moving on to the second stage, criteria design. The key question is how to construct a proper quality label that can capture the true data quality. So first, based on where to get a quality label, we divide the source into internal information and external information. By internal, we mean the quality signals are inherent in the candidate dataset. For example, some works quantify how difficult an instruction is to follow for their backbone and use that difficult as the quality label. That's what we call internal information. The first type of methods using external information will obtain the quality label through external measures like preferences from LLMs. For example, AlphaGases directly prompts GPT with a template to obtain a score for each sample like a clarity score of 3 out of 10. And these quality labels are typically discrete values. The second type of methods using external information measure a sample's influence on model's outputs according to its performance on some external benchmarks. Take instruction GPT as an example. It quantifies a sample's influence by estimating the model's inference loss on external benchmarks and use the estimated loss as the quality label. These labels are typically continuous values. The third and final stage is to verify the effectiveness of the selector. Existing works compare a selective enhanced model against either the baseline model or other popular LLMs using wing-tie loss metrics or benchmark scores. Now we have a framework to categorize the methods systematically, but still we can't directly compare one method against another because, first, different methods vary greatly in their experimental setups. One may use Alpaca as their candidate dataset, while another will choose Vicuna. And more importantly, we don't have any computational tools or metrics to draw fair comparison yet. To address these issues, we propose a unified comparison approach that incorporates ratio-based efficiency and ranking-based feasibility. Here, we formally define the efficiency as a metric that reflects the data selector's ability to accurately identify high-quality data and contribute to better model performance. The keywords are high quality and accurate. High-quality data should improve the model's performance, while accurate selection gives a small selected subset. Combined with the challenges of inconsistencies in experiment setups, we designed these two indicators. the performance improvement ratio, short for PIR, and the selected dataset fraction, short for SDF. The PIR is calculated using the SEM score divided by that of the baseline model, and SDF is calculated using the size of the selected subset divided by the size of the entire dataset. We can plot each method in a graph, just like the green dot and the red dot here. In this case, the green method has a high PIR value and a small SDF value, which means it can accurately select a small amount of high-quality data from the entire dataset, and thus we say it has high efficiency. While the red method selects more data and contributes less to the model performance, so it has low efficiency. So far, so good. But what if the green dot is in the upper right corner and the red dot is closer to the origin? Now it's very hard to determine which method has a higher efficiency. So we further establish an efficiency curve to represent the true relationships between these indicators and overall efficiency, aligning them using extrapolation and scaling laws. Now we can see that the green method is more efficient than the red one. But exactly how much is still not explicit. So the last step, we set a baseline and convert each method's latent efficiency into an explicit signed distance from that baseline. Finally, we can make direct and fair comparison between methods. So here is the actual efficiency plot. As you can see, IFD emerges as the most efficient method, while uppercases is the least efficient one. Unlike previous studies that primarily focus only on efficiency, we also consider the feasibility of each method, which is evaluated using simplicity and flexibility. For simplicity, we consider the following aspects: the number of LLM trained, the number of its selection algorithm steps, and reproducibility, measured by whether it's open sourced or not. For flexibility, we consider whether the model is transferable or extensible. Transferability is determined by whether the model and the dataset can be replaced without retraining. And the extensibility is determined by whether the model relies on ChatGPT like proprietary models. Let's take uppercases as an example again. Uppercases trained 0 LLM for selection because it relies on ChatGPT for quality annotation. And it has 2 algorithm steps according to our way of counting the steps, and it's not open source by the authors, so it's not reproducible. In terms of flexibility, you can change ChatGPT to any other models and change the datasets. It will not require extra retraining or cause a decrease in efficiency. And finally, it's not GPT-free, so it's not extensible. Then, using a weighted sum, we can compare it with all other methods, and in this case, uppercases will rank first in simplicity and second in flexibility. Then, to make the comparison more intuitive, we visualize the simplicity and the flexibility rank, and further assign equal weights to them so that we can review the overall feasibility ranking. And this is the actual feasibility plot of all the methods we surveyed. Uppercases demonstrate the highest flexibility despite its mediocre efficiency. In comparison, although methods like instruction mining outperform uppercases in efficiency, they compromise feasibility due to complex algorithms and heavy LLM fine-tuning. After an overall consideration of both the efficiency and feasibility, we come to the key observation that methods emphasizing more targeted quality measurement achieve higher efficiency at the cost of feasibility. Before we wrap up, here are some interesting trends and challenges. First, candidate datasets change from general ones to more specific ones, tailored to each method's unique backbone. Secondly, quality measurement has seen a shift from early score-based preferences to currently more optimization-aware signals. And the third trend is that selected features shift from concrete ones like linguistic indicators to abstract ones like estimated loss. Okay, progress in the field of data selection is really exciting. So we decided to end the talk by giving a few speculative challenges. First, how to balance the efficiency and feasibility is our key observation and the challenge. Secondly, how to ensure an objective measurement. For methods relying on external models, it's really hard to design an unbiased prompt. The third challenge is how to improve domain performance without compromising others. Typically, a selected dataset that can improve model writing doesn't guarantee better coding ability. And finally, how to satisfy multiple goals simultaneously. As far as we know, few have explored how to handle multi-turn conversations and multimodal scenarios. That's it. Thank you for listening.